Welcome back, my Calc 2 babies, for part 2 of Chapter 8, Section 4 on trigonometric substitution. Now, this is part 2. If you just glossed over part 1 or just gave it a cursory glance, you may struggle a little bit, because what you may end up having to do is pause this video and go back and watch part 1. Again, take some better notes, because really what's going to happen here, it's going to look confusing if you don't know your right triangle trigonometry. But if you understand your right triangle trigonometry and the relationship between the three sides of a right triangle, then and the ability to recognize that relationship, then this goes pretty smoothly. So the game plan looks something like this. So we're given a problem, like, say, example 1. And as you begin this process, you start thinking about, okay, well, what do I have in my toolbox to be able to integrate this? Now, on the first glance, you might think about some of your arcsecant, arcsine, arctangent rules. But this one won't work here because of this x squared. All right, so if we had just an x, then we could go back and use some of those previous integration methods. But because of this x squared, we're going to need a new method. And let's go ahead and see what we can do. So my suggestion is, now off to the right, I have this little cheat that's going to help with the setup. I don't particularly need this cheat if I understand just the basics of my right triangles. But here's my suggestion. When you're going to start these trig substitution problems, why don't you just draw a random triangle and label it? Okay? Because you should be missing one of these sides. Now, let's take a look at what's under the radical in example 1. We have 9 minus x squared, right? So that takes on the form of the square root of a squared minus u squared, right? In other words, this is a problem where we're going to use sine, right? So let me kind of label. So of course this is going to be our point of reference, our angle of reference, theta. And let me go ahead and start to label things, right? So sine of theta is going to be your opposite over your hypotenuse. And what I should be missing here, I should have my opposite side, I should have my hypotenuse side. What I should be missing is that last leg, the adjacent. Ready? So what is opposite of example 1, right? So it's, well, you can refer to this little cheat, or you can think about the relationship, the Pythagorean relationship between the sides of the triangles. But this is going to be, we can think about, in this case, a is equal to 3, and our u is equal to x. So in this case, we're going to have x here, that's our opposite, and the hypotenuse is 3. Okay, now with that setup, I'm going to move this sine of theta over here. So with that setup, if I label those two sides of that right triangle, then all of you would know that you can always get the third side by just setting up a Pythagorean relationship, and this would be our 9 minus x squared. Okay. So at this stage, I'm moving over here to where I wrote sine of theta, and this is how I suggest you you do these problems. Or at least it's up to you, but this is how I think about them. So I'm going to have sine of theta, obviously, is the opposite side over the hypotenuse side. And here, my opposite side is x, and my hypotenuse is 3. Okay? So if you're looking for a playbook, step 1 for me is always draw the right triangle so that I can figure out which type of substitution is going to work. Then, once I know what type of substitution is going to work, this is a sine problem, a sine of theta problem, I'm going to go ahead and plug in, and I'm going to solve for x. So therefore, x is going to be equal to, multiply both sides by 3, so that's 3 sine of theta. Okay. Now, immediately, what we're going to want is dx. Okay, so if dx, if we just take the derivative of 3 sine of theta with respect to theta, we're going to get 3 cosine of theta, and this is d theta. All right, now I'm going to start to box in some of this information that is important. All right, now on the previous video, I showed how once you have defined x to be 3 sine of theta, there's a consequence of this that's going to happen, and what we're going to, you could always, listen, I'm going to erase this arrow, but you could always plug in 3 sine of theta in here for x, square it, and work the math. But what is going to happen, as I showed you in a previous video, is that you're going to be able to rewrite that denominator, which is, or at least not the denominator, but the square root of 9 minus x squared. You're going to be able to rewrite that as 3 cosine of theta. Always. Okay? Now, let me kind of take a glance at what I have and what I don't have. So you and I agree, I'm going to erase this after I circle, but let's you and I agree that I know what to plug in for dx, so that's no problem. I know what to plug in for the square root of 9 minus x squared, so that's not a problem. The only thing that I need to do is plug in something for x squared. And as it sits, I don't have that yet. So I know what x is, so I would have to square that. Therefore, x squared is going to be 3 sine theta squared, which is just 9 sine squared of theta. All right, starting to get a little bit cluttered, so let me erase as much as I can. Okay, and now at this stage, what we want to do is I'm going to rewrite example 1, and then we're going to start to plug in the information, the new information that we have. Okay, so I'm going to draw you some arrows, and then in just a second I'll end up erasing these arrows. Ready? So dx is going to be substituted here. X squared is going to be substituted here. And the square root of 9 minus x squared is going to be substituted here. I'm going to now do that substitution. All right, so that leaves me with 3 cosine theta d theta over 9 sine squared theta times 3 cosine theta. And I would advise that you stop for just a second and recognize what you were able to do. So we started off with an integral that was in terms of x with respect to x. And what we have now is the same integral in terms of angle theta with respect to theta. And our hope, and what will be true, is that this will be much easier to integrate. Just remember, this was a shortcut, right, to use theta. When we're done, we have to get back to in terms of x, right? Our answer, if our question was in terms of x, our answer should be in terms of x. And so let me kind of get rid of these arrows. And I'm going to go ahead and keep going here. All right, so what's nice is at this stage, as soon as you plug everything in, just the way that these problems are set up, textbook problems, is some things should cancel. All right, and let's rewrite what we have at that point. So at that point we have the integral of d theta over 9 sine squared of theta. Okay, and now what I'm going to do at this point is, let me do it, and then I'll tell you what I've done. So to divide by 9 is to multiply by 1/9. So I'm going to bring out this 1/9 out in front of the integral, just to clean it up. That would leave me with 1 over sine squared. And I don't know about you, but I like to have my d theta to the right of my integrand as opposed to in that numerator of that fraction. Not that it matters, it's just structurally I see it better this way. All right, well, let's go ahead and rewrite 1 over sine squared. All right, so 1 over sine is cosecant, right? So 1 over sine theta is cosecant theta. So that would mean 1 over sine squared is cosecant squared. Ready? So I have 1/9 cosecant squared theta with respect to theta. Okay. Now, at this stage, we want to take our antiderivative, right? So we want to integrate this. This, in my opinion, these are we've done the hard work. This should be some reference point, right? We should be able to, like you would look up a formula, we should be able to look up what the integral of cosecant squared is. If you're of the opinion that playing a game of memory to memorize all of these integral formulas is in somehow, some way doing mathematics, then I absolutely disagree. That one is a game of memory, the other is a game of structure and math. And in my opinion, I am not going to waste what space that I have in memorizing trivial things like what the integral of cosecant squared is. So I would look it up, and if I do, it would be let's see here, cotangent, I believe. So let me rewrite. So now we have, I think it's actually negative cotangent. So negative 1/9 cotangent of theta plus c. All right, now I'm going to box this in, although we're not done. So what you have at this point is something very beautiful. You were able to find the antiderivative of that example, but you used a variable of theta to do it. And now what we want to do is get back to the variable x. And this is why at the beginning I mentioned something to you, that you should always draw a triangle. Because this triangle can actually help you get back to x very, very quickly. Right? Because let's go ahead and think about it. How do we define cotangent of theta? Well, tangent is opposite over adjacent, so cotangent is the adjacent over the opposite. So in this case, cotangent of theta, let's look at our triangle. The adjacent side is the square root of 9 minus x squared. The opposite side is x. So do you see what I'm saying? That you can actually use that triangle to get into terms of theta, as well as to get back in terms of x. So what is cotangent of theta? Well, it's the square root of 9 minus x squared over x. I'm now going to substitute that in there. So I have negative 1/9 multiplied by the square root of 9 minus x squared over x. Plus c. And you can clean that. Oh, let me see if I can do a little bit better than that. You can clean that up by getting rid of those brackets, and you can rewrite that all under 9x, but you're done. You have done the calculus that you were asked to do at this point. Okay, so another one. So take a look at example, let's take a look at example 2. And what we want to start trying to get a feel for is what type of triangle can I use to represent that radical, right? So you can always just draw a random triangle. And this appears, looking at this is the square root of 4x squared plus 1, right? So this is going to be a problem where we define u in terms of tan theta. So in this case, we have a situation where u is obviously the 2x in this case, and the a is 1. Now the only difference obviously is we have the 1 where the a should be, and I should say the a squared is where the u squared is, and the u squared is where the a squared is. So if that is a problem to you, if that annoys you, that's not a problem, really. We can always rearrange this to 1 plus 4x squared. Okay, so again, what I'm noticing is based on the setup is that the side that we're missing, I'm hoping that you can do this as well. The side, what I can say about this, the fact that we are adding 4x squared in 1, that tells me the side that we're missing is the hypotenuse. So I'm going to go ahead and write, so if you're missing the hypotenuse, that would mean that you would have the adjacent and the opposite, and that's why tan of theta, which is defined as the opposite over the adjacent, is going to be a good choice. Okay. So let's go ahead and plug in everything that we want into the triangle. So again, this is our theta, and the side opposite to our theta should be our 2x. Our side adjacent to our theta should be our 1. And that tells me that this missing side, the hypotenuse, is the square root of 4x squared plus 1. Okay. So again, this is how I suggest you approach it. So after you have your triangle, let's plug in for opposite, plug in for adjacent. All right, so now we have tangent of theta is going to be equal to 2x over x. No, my apologies. 2x over 1. All right, so 2x over 1. And now what you're going to do is solve for x. So dividing both sides by 2, we get x is going to be equal to 1/2 tangent of theta. Okay. Now I'm going to go ahead and jump to this, what comes out of this fact that if you were to plug 1/2 tan theta in for x. But the good news is I'm going to go ahead and get dx because I don't want to forget about that. So in this case, if dx is going to be 1/2 secant squared theta d theta, right? The derivative of tan is secant squared. Okay, and what I was saying just a second ago was what comes out of this idea, the fact that you are going to define x as 1/2 tan of theta, is that you get to rewrite this radical, the square root of 4x squared plus 1, can be rewritten as a secant theta. Again, last video I showed you how that we get to make that statement. Very, very simple. You could plug in for x yourself and you would see this. Now, I'm going to go ahead and erase that a because in this case a is equal to 1. So the square root of 4x squared plus 1 is simply secant theta. Let me, while we're here, let me go ahead and say just a couple things that mistakes that I see, right, often. So let me change my color to red to represent my red pen, taking off points. So aside from the inability to set up the problem, okay, that is something that is only going to come with some exposure, some practice. But let's assume that you know the general idea and you can get into the nitty-gritty of this method. What I'm going to show you right now is something that is just, it's a trivial mistake, but it happens enough that I'd like to point it out. So a student will automatically know that they're going to be able to use a secant theta, but a lot of times they'll write a d theta right here. Right, so, but you didn't take a derivative. You shouldn't, right? I mean, when you take a derivative with respect to theta, then you can bring that d theta over to the right side like we did here. But that last part, you never took a derivative. So just be careful. Just be careful when you're doing your substituting. Okay, and let's see if there's anything else that we need. I don't think we do. So let's see what happens if I start to plug in some of the information that I've defined. So let's rewrite. So I want to integrate dx over the square root of 4x squared plus 1 with respect to x. All right, so all of these arrows are pointing to the fact that you get to do some substituting, okay? Well, you know what to put in there for dx, you know what to put in there for that denominator. All right, so dx, let's start there. So now we're going to have the integral of 1/2 secant squared theta d theta all over secant theta. All right, and some things should cancel. All right, of course, we can cancel one of those secants. So, and I can even pull that 1/2 out in front of the integral. That just leaves me with secant theta d theta. Okay, well, there's nothing left to do except to integrate. And if you integrate secant, you are going to get 1/2 ln, my apologies, so 1/2 ln of the absolute value of secant theta plus tangent theta plus c. Okay, and we would be all done if we began in terms of theta. We could end in terms of theta, but we began in terms of x. So right now, what you need to do is recognize that secant theta is just the hypotenuse over the adjacent, and obviously tangent of theta is the opposite over the hypotenuse. So I've just teaching, I've been teaching post-secondary for 8 to 10 years. And there are quite a lot of my colleagues I've had at various places that don't have the students draw out that triangle, that very first step. But it just makes it a whole lot easier when with what we're about to do now, okay? We're gonna go ahead and use that triangle to get this back in terms of x. So let's go ahead and finish this guy up. So we have 1/2 ln. All right, now how can I rewrite secant theta in terms of x? Well, what's the hypotenuse and what is the adjacent? So this would be the hypotenuse is the square root of 4x squared plus 1 over the adjacent. I am going to write this adjacent, even though I know it's division by 1, over 1 plus, and now let me go to tangent, so that would be the opposite, which is 2x, over the adjacent, which is, my apologies. Oh, first off, did you notice this? You did, didn't you? You were just waiting the whole time. In case you didn't. This is wrong. All right, let me fix that. I wonder if I actually said it out loud. I probably should go back and actually hear what I said. So opposite over the adjacent, not the opposite over the hypotenuse. Okay, so the adjacent is 1. And plus c, and we're done. Beautiful. You can obviously get rid of those 1s in the denominator, but I hope that's starting to click. I hope it makes sense. That's funny. I sit and wonder how many silly mistakes I've made in these videos, because I'm not going back and editing any of them or looking back at my content. I wonder how many times you've sat there for 3 minutes staring at a mistake like that, thinking, when is he going to notice it and fix it? Well, anyway, So let's try one more. Maybe one or two more. Actually, I'll tell you what. Let's go back to this problem. So at the very tail end of the first video for this section, I posed a problem. I said, look, so the area of a circle, the formula for the area of a circle is pi r squared, right? And we're going to assume that the radius of our circle is 1. So if I plug a 1 in for r, that's just pi. Now, I'm interested in a half circle, right? And I'm going to choose to take the positive, the principal radical, so the top half of that circle. Radius is still 1. Now, what I've written here is, what's the area for the half circle of radius 1? Well, it's just pi over 2. And I asked, can you prove this? Can you prove this with calculus? And I know you were on the edge of your seat back then, but we actually can now. We can do that. You now have the skills to do so. So let's start with the setup of the integral. So we're going to be integrating from -1 to 1. And let's take a look at our radical. Well, that would just be y is equal to the square root of 1 minus x squared, right? So I think you can automatically, right now, you can tell that that looks like it takes on the form of the square root of a squared minus u squared. This is a sine theta problem. So let's go ahead and label. Let's go ahead and label our triangle. So I'm hoping you're getting pretty good at this, but in this case, I would have a hypotenuse of 1, right? Because a is equal to 1. U is equal to x, so I would have a opposite side of x, and then I can think about this missing base of this triangle as the square root of 1 minus x squared. Okay, and now so you should pause the video and see if you can actually get through this. Don't worry about the bounds yet, because that's actually, I need to do more with that. Okay, I'll say that one more time. This upper bound and lower bound of integration is actually great when you're thinking in terms of x. But if you're gonna rearrange your integral in terms of theta, well, you're going to need to adjust your bounds to represent that. So as of right now, you should pause the video, you should give it a shot and see how far you can go. But I'm going to go ahead and pretend that you've already done that and jump right into our problem. Ready? So let's start with some definitions here. So we know that sine of theta is the opposite over the hypotenuse. And I'm going to go ahead and plug in sine of theta. I'm going to plug in for opposite, which in this case, this is theta. So my opposite would be x. And my so my hypotenuse would just be a length of 1. Okay. So at this stage, we normally go through and solve for x, but we're there, right? So we know now that x is equal to sine of theta. Okay. So let's immediately go ahead and take dx. So if we take the derivative of x with respect to theta, derivative of sine is cosine theta, and I'm going to go ahead and write my d theta here. Okay, now the consequence, the result of defining x as sine of theta is that we get to rewrite the square root of 1 minus x squared as a cosine of theta. Of course, a is just 1 in this case. So in other words, just cosine of theta. Okay, so let me kind of just box in all the information that I'm going to be using when I do my substitution. So ready at this stage, I'm going to be substituting in a cosine of theta for this square root of 1 minus x squared, and I'm going to be substituting in a cosine of theta d theta for my dx. So let's rewrite everything. So now I'm going to leave my bounds alone, my upper and lower bounds alone for just the time being. So I'm going from -1 to 1, and this is going to be cosine of theta times cosine of theta d theta. Okay, or in other words, -1 cosine squared. Okay, so it's at this point that we need to address these bounds that are in terms of x, and we need them to be in terms of theta. And this is actually very simple if you'll just pay attention to me for just a second, right? So what I'm going to need to do this is this little guy right here. So since x is equal to sine of theta for this problem, then what I can do is set x equal to 1. So 1 is equal to sine of theta, and then set x equal to -1. And then solve for theta, right? So you're just going to take sine inverse, and we would know that theta, when we know this, when sine is equal to 1 when theta is 90 degrees, right? Pi over 2. And we know that sine of theta is equal to -1 when theta is equal to, well, let's stop. Is it 3 pi over 2 or -pi over 2? Well, it actually is -pi over 2. And that's because, and I'll come right back in just a second, but that's because all of these rules that we came up with here, right, when we were able to define these, but this in terms of theta, but this assumed that theta was between, so -pi over 2 and pi over 2. Likewise, the same thing here, -pi over 2 actually not equal to, just -pi over 2 to pi over 2. Okay? This is, or down here, that last one, this is, remember, we have a piecewise function for this secant problem, for this specific type of right triangle. And if let me just think really quickly, so this should be your theta, should be within 0 and pi over 2 for that top piece of our piecewise. And then the bottom piece applies for when theta is from pi over 2 to pi. All right. Well, actually, it's right here. I could have just referred to I could have referred right to the cheat sheet that we had. So, okay, so I've answered the question about why we chose -pi over 2 as opposed to 3 pi over 2. And now there's nothing left to do except go ahead and replace -1 with -π/2, and replace +1 with π/2. All right, so how do you integrate cosine squared theta? Well, it's probably best to use your power reducing formulas. So in this case, we know that cosine squared theta can be rewritten as 1 plus cosine 2 theta over 2. So what does that mean for us? That means that I can rewrite this as -π/2, from -π/2 to π/2. But instead of using cosine squared theta, I can rewrite that as 1 plus cosine 2 theta. You could also think, so at this stage, well, let me go ahead and finish this problem. D theta. So I mean, I get it that cosine squared is, you could have used your Pythagorean relationship dealing with that it's 1 minus sine squared, but you would still have a squared trig value. So this is the way I'm going to do it for this problem. And now this is easy, right? So if we go ahead and you can just use u substitution here. Let's go ahead and integrate this. So what do you get when you integrate 1 with respect to theta? Well, you get theta. Let me not forget my 1/2, right? Did you notice that too? I knew where I was going with that. So the real formula is 1 plus cosine double theta over 2. I went ahead and brought out the half. So back to where I was. If you integrate 1 with respect to theta, you just get theta. And then if you integrate cosine 2 theta with respect to theta, well, you go through the u substitution process. Let u be 2 theta, du would be, right? So I'm running out of space. My apologies. I'm trying to find some place to work here. How about I free me up a little bit of space? Right, so we can let u equal 2 theta, then du is just 2 d theta. And now I'll have to multiply and divide by 2. So what does that mean for this particular problem? So let me free myself up. I'm crammed in these little places, man. I keep almost making silly mistakes. Plus, ready? So that would just be 1/2, because I have to multiply and divide by 2. 1/2 sine of 2 theta. And now we need to go from could have done this a long time ago. All right, so let me make sure. I don't think I've made any mistakes. But I'm gonna, since I don't have you in front of me to yell at me when I make a silly mistake, I just want to double check that everything is good. So we end up with theta over 2 plus 1/4 sine of 2 theta. And we now need to substitute f of b minus f of a. All right, so when all is said and done, we would get so plugging in pi over 2 divided by 2 would be pi over 4. And then we would plug in pi over 2 into theta for the second term, which would end up being pi, which sine of pi is 0. All right, so this would be pi over 4 plus 1/4 of times 0 minus, all right, now you're plugging in negative pi over 2. So negative pi over 2 divided by 2 is negative pi over 4. And again, negative pi over 2 times 2 is negative pi, which is again 0. So we get pi over 4 plus negative pi over 4, no, minus negative pi over 4, I meant. Which is indeed pi over 2. So what is the area of a half circle of radius 1? Well, it's pi over 2, and now you are able to show that. All right, so I think I'm going to go ahead. You have the gist. You should practice some more of these. But I think what I've given you is enough to get started in some practice problems, and I will see you again soon.